So now we're talking. Now we know what a step function is. We know what an ordinate set is. So now we do definition into the step function. So this definition is constructed so that the integral of the non-negative step function is equal to the area of its ordinate set. That's kind of the most common definition for a step function. So let's go a little bit analytically. So say there's step function S and its domain may to be. And there's a partition such that it has n partitions, which will partition off this into of A and B. Now say that Sk is constant such that in the kth subinterval, what that means is this of x is Sk when x is in an open interval. Sk and so on. Sk. That is basically this. And because there are n partitions, k is equal to 1. So then, how do we define the integral form? Is denoted by the symbol a to b s of x dx. This is the integral of this step function, which is equal to k equals 1 to n. If you already got it, that's fine. So it goes k minus 1. So what this means is basically we add up tiny rectangles. So if there's a value like this, another like this, one like this, this is one partition. So we have x0, x1, x2, x3. So k equal on this. This is the first one, plus second, plus third. Here the value is sk1 plus k2, sk3. And the area of the rectangle is sk1 into x1 minus x1 plus sk2 plus 2 minus x1 sk3 x3 minus x2. And that's the area. And as we go to our function, is the equal to the area of its ordinate set, basically. So there's also another important point to note that if you change or move these values, like for example, you just shift this a little bit, the area will be the same. So that's an important point to note. And yeah, and no matter how fine you make a subdivision, if you add on x dash here, it's still going to add up to the same area. So that's the integral of the step function. Next, we come to the properties of integrals or integral of the step function. Come on, Andrew, oh man, you're way far behind it. So then we have few theorems. We'll prove them in the exercises also, I think. So maybe f of x plus t of x dx. It was all high school basically. What you go into one detail. This is the additive property. Then we have the homogeneous surprise polynomial H1 more GE NUS property, which is basically for every serial number C. So we need to have this. Okay, just later. That's real number. let's see, then we also have the linearity property, which is basically additive and homogeneous property. Z control. Anyways, I think C2 on the thing. Except for the x step functions. Then we have the comparison theorem. That is f of x less than the step function t of x. For all x in its domain, say a to b, then the integral of this is less than the integral of t of x for all points. So basically, integral is for all points. But yeah, basically, you can think of it as like the ordinate set. All these ordinate is less than this ordinate points. So then the sum of all these ordinate points will be less than the sum of all those ordinate points, basically. And then we have the additive property of area, which is and then we have variance under translation property, which is basically so you have a of x dx. This is also quite intuitive once you understand it. So basically, we have a function, right? So this is a, this is b. So then you have a new one, say a plus b, and b plus c. So when you take these limits, so this is x dx integrate, right? So then where x is a member of, I mean, x is a member of this, and this interval. In the same way, you take this function, new function, where this x is a member of a plus c to b plus c. And then you break it into partitions and all that. That comes into proof. So basically, these two are the same, but this has its interval from a plus c to b plus c. So then if you take this point here, this minus c is a, and this minus this is b. But then the area is nearly the same. It's the same. So yeah, that's basically that in variance and translation. And then you have the expansion or contraction of the interval of integration in this kind of property. So this basically say we have limits k to kb of integration. Yeah, this is equal to Intuitively, what this basically means is like you have this function, so you multiply it, yeah, this function, which is basically this, and now we have a number, let's say twice this and twice this, which is a lot here, and this the area of that. So you can prove that this longer area is k times that. So more to get it understand more diagrammatically, you can just show like this. There is A, there is B, and here some X. Now this is 2A, and this is 2B. This is 2X. So you can clearly see this is twice that. So analytically, you can prove it, and that's more intuitive. Yeah, so that's